Hello everyone, in this lecture we will discuss about Sherwood number. In the previous lecture we have discussed about Reynolds number, Nusselt number, Prandtl number. Now in this lecture we will discuss another number which is a dimensionless number and which is called the Sherwood number. Now the Sherwood number is a dimensionless number which is very important and useful number in mass transfer. It is very useful in convective mass transport and molecular mass transfer process. Now before the discussion of Sherwood number, we have to discuss the Fourier law and the Newton law of cooling, and we should discuss the Nusselt number. Then from the analogy we will discuss the Sherwood number. Now from the Fourier law of heat conduction, the heat rate is equal to K into area to dt by dx. Suppose we have a wall. This is a wall. This is the thermal conductivity of the wall. This is a high temperature. This is the lower temperature. The heat transfer from the higher temperature side to the lower temperature side, and through the wall the heat transfer through conduction process. And the Fourier law for the heat conduction is Ka dt by dx, and this is the cross-sectional area for the heat transfer. This is the cross-sectional area for the heat transfer. This is the cross-sectional area for the heat transfer. The cross-sectional area for the heat transfer is A. Now we know that the heat flux is heat rate divided by area is nothing but the heat flux, and it is K dt by dx. Similarly, from the Newton law of cooling, which is used for convection heat transfer, which is heat rate, heat transfer coefficient into area for the heat transfer into dt. Now the heat rate, the heat flux will be equal to heat rate divided by area is equal to H into dt. Now there are two types of convection process. One is the natural convection process, and the other is forced convection process. Now in the natural convection process, due to density difference, the heat transfer will take place. Due to density difference, suppose we have water in the container. Suppose this is the water. If we give some heat to the water, then the lower side molecule of water will become hot. Its density will decreases and it will transfer to the upper side in the container. And similarly, the upper side water molecule, which is higher in density, it will come down to the container, and circulation and current of natural convection will take place in the container. So this process is the natural convection. There is another heat transfer, convective heat transfer process, which is the forced convection process. Suppose we have a hot metal. Suppose it's a hot surface or hot metal surface. It is placed on some surface. If the heat, and suppose this is the air, flowing air. Now the heat transfer to the air is by natural convection process. Now if someone is interested to increase the heat transfer, then now if we want to increase the heat transfer, then we will put some fan or blower or fan. So the heat transfer is enhanced in this case by the fan or blower or some compressor or some other external sources also. In this case the heat transfer is increased, and this type of the heat transfer is called the forced convection heat transfer. Due to the forced convection heat transfer, the heat transfer coefficient is very increased, and hence the heat transfer rate and heat transfer flux also increased in the case of forced convection as compared to the natural convection process. In natural convection, due to the density difference, the heat transfer takes place. Similarly, in the forced convection, due to the density difference and also due to high velocity of air, the heat transfer are taking place. So the heat transfer in the forced convection process is very high as compared to the heat transfer in the natural convection process. Now, similarly for mass transfer process, there are two types of process. One is molecular process and the other is convective process. Now for molecular diffusion, there is a famous law which is called the fixed law of molecular diffusion. Now the fixed law of molecular diffusion is for the molecular level. The molecular process is very slow process and it is called diffusion, and the convective process are fast, and the mass transfer rate in the convective process are very fast as compared to molecular process. Now the molecular diffusion is discussed by the famous law which is called the fixed law of molecular diffusion. Now the fixed law of molecular diffusion, the theoretical form is Na. The molar flux of component A is equal to the diffusivity of component A into the component B into the concentration gradient, and this is the fixed law of molecular diffusion. Suppose we have two types of molecule. Suppose we have two types of gas molecule. Suppose we have two types of gas molecule, molecule B and molecule A. Suppose these are the molecule A. Suppose we have two gases. Suppose one is nitrogen and hydrogen, or it can be hydrogen into helium. Suppose we have two types of gases. One is gas B and the other is gas A. Suppose the gas B is stationary and its flux is 0, and the A is diffusing into the gas B. Suppose this is the gas A molecules. The gas A is diffusing into the gas B, and the gas B is stationary. So in this case, the fixed law of molecular diffusion will be written as Na is equal to minus dAB, the diffusivity of gas A in the gas B, and the concentration gradient This dCA by dZ show that this dZ show us the length of the diffusion path. So this is the dZ. Now and the CA, suppose the dCA show the concentration gradient. It show the concentration. Suppose this is the point A and this is the point B. The concentration of A at the point 1 is CA1. Similarly, the concentration of component A at the point 2 is CA2. So CA1 minus CA2 divided by this delta Z is called the gradient of the concentration, and when it multiply by the diffusivity of component A into the stationary component B, we will get the molar flux of component A in the stationary component B, and it is called the fixed law of molecular diffusion. Now similarly, the fixed law of molecular diffusion can also hold for liquid. Similarly, the convective mass transfer are also taking place in the liquid and gases. For example, suppose we have a container. Suppose we have a container which is filled of water. Suppose we have a container of water. We have a container of water. Now suppose we put some crystal of sugar crystal. Suppose we suspend a sugar crystal in the container of water. Suppose this is the sugar. Suppose we suspended the sugar crystal in the water, in the beaker of water. Now we know that the concentration of sugar near the crystal will be high, and the concentration of sugar at the bottom and at the top will be small as compared to the concentration of sugar near the crystal. So the sugar will dissolve in the water. Its solubility will be very high near the sugar crystal. So the sugar concentration will be very high at this place. As we increase the depth or height, the sugar concentration in the water will be decreased. So the concentration of sugar in this place will be small as compared to the concentration of sugar at this place. So due to the concentration gradient, the sugar molecule or the sugar solute molecule will be transferred in the water. It will be transferred from the higher concentration region to the lower concentration region in the water, and due to this concentration gradient, the mass transfer will take place in the beaker. Now suppose the concentration of sugar near the crystal is denoted by Ca1. Similarly, the concentration of sugar at the bottom of the container will be denoted by Ca2. So there is a concentration gradient between the sugar molecule. So due to this concentration gradient, the sugar molecule or the solute molecule will be transferred from higher concentration region to the lower concentration region, and it is called the concentration gradient. Now due to this concentration gradient, the mass transfer will take place, and it is called the natural convective mass transfer process. This process is called the natural convective mass transfer. Natural convective mass transfer, like the natural convective heat transfer. For the natural convective heat transfer, the change in density is the driving force. Similarly, is the driving force for the heat transfer. Now, in the case of mass transfer, the change in concentration is the driving force for the transport of solute molecule in the solvent, and it is called the natural convective mass transfer. Now situation arises where we need a high mass transport process. Now there are some situation arises where we need high transport of molecules or high mass transfer rate. So we need some external agent to increase the mass transfer rate. Suppose this is a water, and we suspend sugar crystal into it. The sugar crystal is suspended in the water beaker. So this is the water beaker, and this is the sugar crystal. Now the string is fixed string. Now due to the concentration gradient, the natural convective mass transfer process will take place. Now if someone is interested to increase the mass transfer rate, then he will put some stir in it. Now if we put some stirrer in it, If we put some stirrer in it, then it will increase the mass transfer rate. It will increase the mass transfer rate, and it is called the force convective mass transfer. The force convective mass transfer. So the force convective mass transfer increase the mass transfer rate many times as compared to the natural convective mass transfer. Similarly, the force convective heat transfer process increase the heat transfer rate many times as compared to the natural convective heat transfer process. Now, as we know that the molecular transport of component A is denoted by the Fick's law of molecular diffusion, which is Na is equal to minus dAb dCa by dZ. Suppose this is equation number 1. Now, the convective mass transfer, as we have already discussed, that suppose we have a beaker, we put some sugar crystal in it. This is the water molecules. The sugar will dissolve in the water, and due to the concentration gradient, concentration in this place is very high. Concentration of sugar in this place is very high, and the concentration of sugar in this place is very small. Suppose the concentration of sugar in this place is Ca1, and suppose the concentration of sugar at this place is Ca2. So due to this concentration gradient, the mass will transfer from the higher concentration region to the lower concentration region. So the molar flux of component A will be directly proportional to the concentration gradient in this case. Similarly, and this is the convective mass transfer. So in the convective mass transfer, the molar flux is directly proportional to the concentration gradient. Similarly, the molar flux is directly proportional to the area for the transport of molecule. If the area for the transport of component A is increased, then the mass transfer will be increased. If the transport area for component A is decreased, then the mass transfer will be decreased, the flux will be decreased. So we can write these two relations into one relation, which is, and we can also write that Na is equal to constant area delta C. So this is the relation for the convective mass transfer flux. Now from the Fick's law of molecular diffusion, the molar flux is denoted by minus dAb dCa by dZ. Suppose this is equation number 1. Now for the convective mass transfer process, the flux is equal to Ka into change in the concentration. This is for the convective mass transfer flux. Convective mass transfer flux is the mass transfer coefficient. This constant is called, this K is called the mass transfer coefficient. Mass transfer coefficient. For liquid, the mass transfer coefficient will be different. For gases, the mass transfer coefficient will be different. So this is the mass transfer coefficient, this is the area for mass transfer, and this is the concentration gradient. Now this is the molar rate, this is the mole per unit time. So the molar rate when divided by A, we will get the molar flux, which will be equal to K into change in concentration. So the molar flux is equal to K mass transfer coefficient into the concentration gradient. Similarly, the molar flux in this case is dAB dCA by dZ. So from the Fick's law of molecular diffusion and from the convective mass transfer, the molar flux from the molecular diffusion, the molar flux is Na, which is minus dAB dCA by dZ. Similarly, for convective mass transfer, the molar flux is Na. Suppose the molar flux is Na dash, and it is equal to K change in the concentration. This is the mass transfer coefficient. Now we know that this is the molar flux and this is also the molar flux. So now suppose this is equation number 1, suppose this is equation number 2. Now divide equation 2 by equation number 1. Molar flux will be equal to minus dAB dCA by dZ. This will be equal to K change in the concentration. So this cancel with this. We obtained this is a constant and this is also a constant, so we will get some other constant value. So constant will be equal to, in this case, constant minus dAB dCA by dZ divided by K into change in the concentration. Now this dZ can be denoted by, suppose this d is denoted by dZ, suppose it is denoted by L, suppose it is equal to L, then minus dAB will be equal to Ca2 minus Ca1. Change in concentration will be equal to dCA will be equal to Ca2 minus Ca1, and the dZ is denoted by L. Suppose it is denoted by L, so it will be L and it will be K. It can also be written as dAB into the concentration gradient divided by the this is also changing the concentration and the concentration gradient. So this will cancel with this and it will be L into K, and this is the constant. So constant is equal to dAB divided by LK, or we can also rearrange this relation by LK divided by dAB is equal to 1 over constant. 1 over constant mean constant, and this constant is called, and this is a dimensionless number which is called Sherwood number, which is denoted by SH. So KL divided by dAB is a dimensionless number which is called Sherwood number, and it is very important dimensionless number in the mass transfer process. As we have already discussed in the heat transfer, that Nusselt number is denoted by HL divided by thermal conductivity K. Similarly, in the mass transfer by analogy, the Sherwood number is equal to this is the heat transfer coefficient. So for the mass transfer coefficient, so in the place of heat transfer coefficient, we will write the mass transfer coefficient. It is L. This was the length of the stationary layer. It was temperature 1, it was temperature 2. Similarly, this was the length for the heat transfer. So in this case, we will also use the length for the mass transfer, and in the heat transfer we use thermal conductivity. Similarly, in the mass transfer we use molecular diffusivity or diffusivity of component A into the component B. The value of this diffusivity will be obtained from graphs, or it can be obtained from various tables, or from the experimental correlation we can obtain the diffusivity of component A in the component B for various gaseous pair, and for the liquid molecules, and for the various liquids, and for various gases. This diffusivity can be obtained from the table and from the various correlation. And this is the mass transfer coefficient. This is the length. This is the length for the mass transfer, right? This is the length for the mass transfer, delta Z. Ca1 concentration is 0.1 and concentration is 0.2, and this was the concentration gradient. So this is the length for the mass transfer. This is the length for the heat transfer. This is the thermal conductivity. This is the diffusivity of component A in the component B, and this is the heat transfer coefficient. This is the mass transfer coefficient. So by analogy, we can obtain Sherwood number from the Nusselt number. Now the Sherwood number show us the convective mass transfer to the conductive mass transfer. It is the ratio between convective mass transfer to the conductive mass transfer. If the conductive mass transfer or the diffusivity of component A in the component B will small, if the diffusivity is small, then the Sherwood number will be very high. If the diffusivity is very high, then the Sherwood number will be very small. If the convective mass transfer coefficient is very high, the Sherwood number will be high. If the convective mass transfer coefficient is low, then the Sherwood number will be small. So the Sherwood number is a dimensionless number, and it is very important in the mass transfer. Now there is another. Now from the heat transfer, we also obtained Prandtl number, which is denoted by PR, and it was the momentum diffusivity divided by thermal diffusivity. Similarly, by analogy, in the mass transfer, there is another number which is called Schmidt number, and it is denoted by SC. It is the Schmidt number, and it is the Prandtl number is the momentum diffusivity divided by thermal diffusivity. Similarly, in the mass transfer, by analogy, there is another number which is called the Schmidt number, and the Schmidt number is the ratio between the momentum diffusivity divided by the to the mass transfer diffusivity, or the mass transfer diffusivity, and the momentum diffusivity is denoted by the kinematic viscosity. It is obtained from the velocity gradient, and it is obtained from the Newton law of viscosity. The mass diffusivity is obtained from the Fick's law of molecular diffusion, and the mass diffusivity is nothing but it is the diffusivity of component A in the component B, which is obtained from various table and correlation. And this is the momentum diffusivity, which is nothing but the viscosity divided by density, viscosity of the fluid, density of the fluid, and it is the diffusivity of component A in the component B. And the ratio, and this ratio is called the Schmidt number. So if the momentum or the momentum diffusivity is high, the Schmidt number will be high. If the mass diffusivity is high, then the Schmidt number will be small. If mass diffusivity is small, Schmidt number will be high. If momentum diffusivity is small, Schmidt number will be very small. So Schmidt number show a relation between momentum transfer and the mass transfer, and it is also a very important number in the mass transfer and in the distillation and in other mass transfer processes. So there is analogy between the heat transfer and the mass transfer. By analogy, we can obtain the Sherwood number from the Nusselt number. Similarly, Similarly, from the Prandtl number we can obtain the Schmidt number by analogy, which is the important dimensionless number in the mass transfer processes. So this is all about the Schmidt number, Sherwood number, the Prandtl number, the Nusselt number. These are all about the dimensionless number. Thanks.